Now let us take a mathematical definition of a vector field. To be conservative, if we can find a scalar function f such that capital F, or the vector field, is the gradient of this scalar function, and for our basic course we shall assume that the function has even the second order continuous partial derivatives. So now in the conservative vector field, suppose that we are given a smooth path, okay, and we would like to compute the line integral of such an f along this smooth path from a point A to a point B in this vector field. That is, so here we have a smooth path from a point A to a point B, and we would like to compute the line integral. That is, we would like to compute the line integral of f using a given path r, and of course the components of r are functions of a single variable t. So now we are computing this integral, this line integral from A to B, and of course that can be written like this. And let's put the values in here now. So who is f? For this example, our f is this, the gradient of the little f, okay? All right. And dr dt, of course, would be what? Dx dt, dy dt, dz dt. So let's write them down. Dx dt, okay, dy dt, and then dz dt, okay, and then we have this equal to, or let's write it in the second line, that this integral will equal, we should take the dot product, okay, what that will become, that is simply going to become df dx, then dx dt, right, and then df dy dy dt, okay, and just a moment, and then we have df dz dz dt. All right. Now, who is this? By chain rule, this is the derivative of f with respect to t when we are going along the curve, right? So what happens here is, okay, excuse me. So what happens here is then that we have this whole thing will be df dt simply, right? And then we got dt, and what does this become? This simply becomes a df, right? Okay. And that will be f at b minus f at a, right? So what happens here is that if we look at this line integral, it only depends on the value of the potential function. I forgot to say that f is called, of course, if it is available, okay, the potential function, or we may say up for potential function of f, because when you integrate, or okay, let me just write here, okay, good. So this is what we have obtained, that the value of this line integral, they depend only on the difference of the values of f at the end points. So what happens here is that doesn't matter who dr is, if f is gradient of f, then what will happen is, doesn't matter which path you take, all that matters is that what the values of f at the endpoints are. So in this case, what will happen? Doesn't matter which path you take, work done will be the same. Or in other words, also, if you take line integral along a closed path, that will become fb minus fb, that is 0. So whenever you are taking, sorry, f dot dr along a closed path, that will always come out to be 0 for a conservative vector field. And now we are going to define another operator. That is, say if we have a vector field whose components are f1, f2, f3, let's just assume a condition which will be true in our basic course case. Okay, later on, you may work with or without these assumptions, but right now let's assume that these are true. So say I have a vector field, then I can define what is called the curl of f, okay, and it is denoted by this expression, okay, delta cross, and of course this f should have been this f. I don't know why I am in a hurry. Okay. So it is denoted by this delta cross f, and keep that, keep one thing in mind, don't treat that as a vector quantity. It is simply an operator, okay? And the way you write it as is that you have let me just write it and bring it back to you, okay? So here it is, just written out. And remember this, a reason for writing it like this is that we have this delta, this is a vector operator. So as I said, it is a vector operator, not a vector quantity. So if you look at this, then you may display it as, and it should be displayed like this, just only this way. Don't switch the positions around. All right, so here what I have is ijk, all right, and then I'll have ddx, okay, ddy, all right, and then ddz, a partial with respect to z, and then we will have what? f1, f2, and f3, okay, and if you expand it, you shall see that you get the same quantity as you have in here. So this is computationally convenient, especially if you are making a hand calculation, which we should in some basic cases. So let us take up an easy example. That is, say we are given, actually, this is the vector u. We are given this vector field, and we want the curl of this vector field. So what that will be, I'll have this, right? Then what happens is, in the first component, what we have is, we have the cofactor of I. So if you look at the derivative of 0 will be 0, then that of y with respect to z will be 0. So the difference would be how much? That will be simply 0. Let's go to the second component. So we'll ignore this and we shall write the difference of dx dz, which will of course be 0. Then d0 dx will be 0. Now we go to cofactor of k. Now here also, since this is the derivative of y with respect to x, that of x with respect to y, that is 0 as well. So curl of the vector u is 0. Now let's take another example right here, okay, in which we just make a little change. That is, what we do is change this to say w, all right. And here what I'm doing is that I am taking this vector field to be, okay, say I took it as y, or say negative y for example, then x 0, okay. So if I did that, what will I get here? Okay, yeah, this will be example 2. Okay, so what I'm going to get is, this is negative y, this is x, this is 0. So again, if you look at cofactor of I, that will be 0. Then go for j, that will be 0 again because dy dz is 0. Now here the situation would be different because dx is 1, then minus dy of negative y is negative 1, so the 2 will add up to 2. So this curl is 0 and this is non-zero. And let's quickly see how would the vector fields of the two would look like. So here we have u, and what we have is that the curl of u is 0. And here we have w, and the curl of w was what? I think 0, 0, 2. So in this case, you can see that there is no rotation created while we see a clear rotation here. It will not be as clear in all the cases. But anyways, so and here the curl is not equal to 0. So later on, you shall see curl as a measure of rotation of a vector field. Now, let us go ahead and see what curl of a conservative vector field is. And remember, a conservative vector field F is a vector field such that it can be written as the gradient of a scalar function. And what we took just one condition out on our function for this course, that the second partial derivatives of the function exist. Okay, they all exist and they are continuous. Okay, all right, so that the order of the derivative doesn't matter. Remember, that was a condition for the order not to matter. So we have this, and what we are going to do is now we are going to write the curl of f. So let's write the curl of f here, see what it comes out to be. Okay, so curl of f is, that is we have I j k, then we got ddx, ddy, ddz. Okay, all right. Okay, so here you go. All right, I don't know why am I rushing. I should go slow. You can always fast forward if you want. Okay, so we got ddz. Okay, and then what happens is, here we have the components, df dx, df dy, right? And then df dz, right? Okay, so here what we have is this vector. So first, when we look at the cofactor of I, we are going to ignore this column and this row. So I shall differentiate df dz with respect to y. So that will be what? The second derivative of f, right? First with respect to z and then with respect to y, right? So, and here we write that in the opposite order. So we will write it like this here. And then what happens in the second part, because we are considering this portion here as the first component, so we have minus, and again we have the same thing, but the orders do what? They reverse, because here first we are differentiating with respect to y and then with respect to z. So what you saw was d dz acts on df dy. And then when you go to the cofactor of j, what you will have first you will have this part here. So which will be, I'll just change the values here. So what happens here? First we have derivative with respect to x, then with respect to z, and then minus the same thing. Now the order reverses, right? Because if you see here, first we are doing it with respect to z and then with respect to x, right? And then at the end, what we have is, that is, we are looking at the cofactor of k, so we shall concentrate on this 2 by 2 determinant. So when we go this way, what we have is d2f dx dy, right? So d2f dx dy minus d2f then dy dx, right? And because, as I said, we are assuming that f has continuous second order partial derivatives, the orders don't matter in here, and this will come out to be simply what? The zero vector, okay? So this is 0. So what we see is that if we take a curl of a conservative vector field, or in other words, like curl of a gradient vector, then we shall always get a 0, right? And if we want to look at the converse, then if, so what we saw was conservative implies, or let me just do this, f is conservative, okay? That implies that f is what? The curl of f is 0. Let's put the simple language. Curl of f equals 0, right? Okay. And what happens is this, that if the components, sorry, of f are continuous everywhere, okay? So if they are continuous everywhere, okay, in our region of interest, then what will happen? You can see that if the curl is 0, then that will imply that f is conservative, okay? That is, you should be able to find a scalar function little f so that, or rather such that, capital F is gradient of that function little f. So let's take some examples here, okay? So the first example that I'm going to take, all we are doing is that we are taking, excuse me, the examples that are a little more involving than the two simple examples that we did. So first, let's take up this example. So here we are taking an example from our textbook. All that we have to do is to check if this is conservative, okay? And the way we will do is, one test would be this, that is, we shall go ahead and compute the curl of f, okay? And if that is 0, then it will be conservative according to our, I mean, if that is not equal to 0, we know it's not conservative, okay? That we know for sure. So let's look at this one, okay? That is, we have ijk, okay? Then we have ddx, okay, d dy, so d dx, d dy, and then we have d dz, and then we got as components what we got, y to the x, right? Then e to the negative x, and then we got 2z, okay? And if we write it out, what we shall have is, we shall have, first we have dz dy, which you know would be 0, okay? All right, let me not do it just verbally because then I'll make a mistake. Then we have dz ddz of e to the negative x, that will also be 0, right? Okay, sorry. And then we have ddz of y to the ex, okay? All right. And then we got minus d dx of 2z. All of them are turning out to be 0 so far, right? Yes, 2z. And now we are about at the end. Okay, now we have d dx, okay, of e to the negative x rather. So it's e to the negative x, and then I have minus d dy, okay, y to the x, right? So this is the condition or the situation that we have, all right? And I was just noting something awkward. I just mistyped it, so let's just type it properly here. So negative, this should be negative x. I'm sorry about that, okay? So what the curl of f is here? The curl of f is, okay, that is, we have 0 from this, 0 from this, and then we got what? We got negative e to the negative x here, and this one is with respect to y, right? So here the derivative of y is 1, and this will stay the same. So what we will get eventually here, we'll get 0, 0, then negative 2 e to the what? Negative x, right? And this does not turn out to be 0, right? So this is not equal to 0. So what shall we say is that this vector field is not conservative, right? So f is not conservative. Okay. Now, so then let's take the next example from the book itself. So here we have this vector field, and what we want to do is that we want to calculate the curl, okay, just to check if this could be whether this is not conservative, right? Or in this case, you can see that all the components are continuous, okay? So if the curl is not 0, then it's not going to be conservative, right? Okay, and there we go. So let's write the value of this. So first what we have, d dy of sine z is 0, right? Then when we look at d dz of x cosine xy, that will also be 0. So this is 0 minus 0. Let's look at this cofactor. ddz of this is 0. ddx of negative sine z is 0. So that is also 0 minus 0, right? And then we are going to look at the cofactor of k. So if I look at the derivative with respect to x of this, what shall we get? Well, first we will here, or let's just write it out. We don't have to do it verbally. Okay, so we are writing this, okay, and then minus we have ddy, right? And then what we have is y cosine of xy, right? And I mean, you may see by symmetry that they are going to be identical quantities. But anyway, let's just go ahead and write it out. Okay. So here, if we use the product rule, we get cosine xy, then minus x times, we are differentiating this, right? And I took minus because derivative of cosine will be negative. Okay. So since we are working on it with respect to x, I'll have y coming out as a coefficient by chain rule, and then what will I have? Sine of x y here, right? And then when we write this down, we will have exactly the similar situation. As I said, by symmetry, we could observe right there, and then minus y, and then x is behaving like a constant. So when we use the chain rule, that will factor out, and we get this. So what we have is these two quantities are identical, so they will cancel each other. And what you find is that the curl of f is the zero vector, right? Now, in this case, as I said, the components are continuous, so we should be able to find, and in our course, they will always be for our regions of interest because we are not going beyond that. So we would like to find a scalar function whose gradient is this, right? So what do we want to find? We want to find a scalar function f, right? Such that the gradient of f equals, meant equals this vector, okay? All right, or in other words, what we have is that we would like gradient of f to be that vector, right? And you know that gradient of f is what? The gradient of f is df dx dy df dy dy dz, all right? So I can go and bring them back for you, but let me just write them out, okay, because it will take me longer. Well, this will definitely take me longer, okay? So we got this, then we got df dy, okay, and then we got df dz, right? So what we have is we have to find a function f such that df dx is y cosine xy, right? df dy is x cosine xy, right? And df dz is, negative sine z, okay? So when we go in search of that f, look at right this here. This is the partial derivative of f with respect to x. So according to this, what f will be is, and again, f is a function of x, y, z, and this is its partial derivative with respect to x. So what we have to do is we just have to obtain the antiderivative of this with respect to x, which simply means that we will treat everything other than x as a constant here. So it's like this. Say we are integrating, say, cosine of 2x, where y is 2. So what happens when you do apply the chain rule, okay, or rather substitution rule, y dx will become the differential of this, okay. So what happens is that the integral simply should be treating y as a constant, sine of xy, and then I have to write what? I have to write a constant. Now here, any function of yz is going to be treated as a constant here because the function is a function of xyz, and when we are writing arbitrary constant here, we are looking at constant only in terms of x, so it can be a function of y and z as well, right? So this is what we got so far. Now we have to determine who g is. For that, we got this information here. So f is, okay, let me just write it in like shorter form. Okay, so we got all this. Okay, and that's just too much there. Okay, so we have, sorry, fxyz is this, right? So what happens is if we write df dy, okay, df dy, all right, then what that will be here. We are differentiating with respect to y, keeping x as a constant, so that will factor out, right? And what do we get? X cosine of what? xy, right? And then plus, we will simply get dg dy, right? So let's write that down, dg dy, okay? I shouldn't really have dragged it so far out, but anyways, I did, so I did. All right, so what we just found is, we found this, right? But on the other hand, we know df dy is x cosine xy, right? So if we set these two quantities equal, okay, let me do that instead of being lazy. So if we set this equal to this quantity, then what turns out is that dg dy is 0, okay? All right, now g is a function of y and z. So if dg dy is 0, that means that g is the constant in y, not necessarily in z. So in that case, what will happen? G will turn out to be a function of z only, right? So g is a function of z only, and so what we got for this is, for f now is, we shall replace g by this, right? And now we are going to utilize, where was the third condition? Dx dz equals, okay, that's a typo and it's too bad I make them, okay? So we are going to use this, right? So we have what? We got df dz equals, of course, this part would be 0, and this is simply h prime of z, right? Because z is the only one here. So if I compare these two, then what does that indicate is that h prime z is negative sine z. So if we obtain our hz, then we just have to take the antiderivative of sine of z, and antiderivative of sine of z would be negative cosine z, right? And then plus an arbitrary constant. So our potential function would be what in here? So if we want, then we can see that this is our potential function for who? For our f equal to this vector, okay? And we can just quickly check. If we differentiate this with respect to x, we will get y cosine xy. This will be 0. With respect to y, we will get x cosine xy. So that is correct. Then the derivative with respect to z, this will be 0, and that will be negative sine z. Okay, so we shall go further in other videos. All right, so let me know if you have any questions.